Okay, we are going to now talk about dealing with exponential and logarithmic equations. Now, the main point, what makes this work, is that exponential functions are one-to-one. So if we have two exponentials equal to each other, and they have the same base, then the exponents must also be the same. So, for example, we have 5 to the x is equal to 125. Well, 125 could be rewritten as 5 to the third. So then x must be 3. And if we have 5 to the 2x is 5 to the x plus 1. Notice that you're both the same base of 5. And that means 2x must equal x plus 1, which means x is 1. And if we have 5 to the x equals 25 to the x minus 1, I mean, you don't notice those are how similar those are at first, but it occurs to you at some point that 25 is equal to 5 to the second to the x minus 1. So you can multiply through the exponents. 5 to the x equals 5 to the 2x minus 2. Well, then x is 2x minus 2. And so to solve that, x equals 2. And you can plug in, check, 25 to the 2 minus 1, 25 to the 1 equals 5 to the 2. That's a true statement. Now, usually we're not able to match them up quite that nicely, but fortunately we have a function that undoes exponents, and that's the logarithm function. So if I see an expression like this, 3 to the x plus 2 equals 7, how do I get that x out of the exponent? Well, I use a log. I say, okay, the equation is 3 to the x plus 2 equals 7. I'm leaving myself a little bit of space here. As this is saying 3 to the something equals 7, and that's kind of how log is defined. So I'm going to hit both sides of this with a log base 3. Those are gone. I'm left with x plus 2 equals log base 3 of 7. So x equals log base 3 of 7 minus 2. Or if you prefer, natural log 7 over natural log 3 minus 2. Now, I want to emphasize that this is a number. If you could think of an easy way to say, oh, 3 to what power is 7? If there were an obvious number there, then you would rewrite in that form. As is, this is still a number of some sort. You know, if we were to graph the log base 3 function, then we'd say, plug in 7 here, and whatever that number is, it's clearly a spot on the graph. It's the y value, but it's irrational. It's not something that we can write in any terminating decimal. If you wanted, you could plug this into a calculator and it would give you that it is about negative 0.2287566. But that just keeps going. So, generally speaking then, we want to leave it in logarithmic form. We don't want to write it as a decimal unless we're asked, because decimals are always rounded off. Log base 3 of 7 is a specific number where if you took 3 and raised it to that power, you would get 7. And you can't really express that in any other way that's simpler. You can round it, but that's all. So yeah, if the log doesn't come out to something easy that you can do by hand, it's best just to leave it in that form. And so I'm just going to run through a bunch of examples here just to give you an idea of what's going on. 8e to the 2x equals 20. And you can feel free, if you like, to pause and try to work these out on your own before I show you the solutions. 8e to 2x equals 20. Now remind you of order of operations. Parentheses, exponents, multiplication, division, addition, subtraction. This is the order of operation you use when you plug in a number for x and simplify. If we're doing the opposite here, we are starting knowing that it equals 20 and trying to work backwards to find x. So we do order of operations in reverse. So, are there any additions or subtractions? No. Are there multiplications or divisions? Yes, there's an 8. So let's undo that 8 with a division. E to the 2x equals 20 over 8, which reduces down to 5 over 2. Now we need to undo that e. Now e is an exponent. E to the power is an exponent, so that's the layer we do it at. The 2x is in a sort of invisible set of parentheses, so that goes last. So I'll put natural log on both sides. So we get 2x equals natural log of 5/2. Then I need to divide by 2. X is natural log of 5/2 over 2. And there's a few different ways you would write this. If you prefer, you can write it as natural log 5 minus natural log 2 all over 2. Those are equally valid answers. I'm not preferring one over the other. But this is an exact answer. If you were asked for a decimal, you would type it into a calculator and you get it's about 0.458. And I understand why sometimes you feel like you'd prefer a decimal, especially if you're doing some sort of practical application where you need to, put on a graph or measure it or something. But if you're not asked, then let's go ahead and just leave it in that form. Check, make sure I'm recording. Yes, I'm still recording. Okay, so this is just another tool that is a typo. I'll fix it in the notes. This is e to the 3 minus 2x equals 4. Now, as I said, exponent, it's an exponent, so we undo it with a log. So we put natural log on both sides. The log and the exponent have to have the same base. Natural log has a base of e implied, so that works. 3 minus 2x equals natural log of 4. And we minus 3, we minus 3. We treat ln of 4 as a number, so we just treat it the same way we would any other number when we're solving an equation. Natural log of 4 minus 3, that is just natural log of 4 minus 3. Divide everything by negative 2. And so we get x equals natural log 4 minus 3 over 2. I think you can simplify this one a little because 4 is 2 to the second. And we know exponent rules or logarithm rules say an exponent can come down front as a multiple. So we get 2 log 2 minus 3 over 2, which we can then split ln of 3, ln of 2 minus 3/2. And I think I may have lost a sign somewhere. I have a negative 2 here. This should have been minus. That should be plus. So this is minus. That's plus, minus, plus, minus, plus. There we go. That's better. And so what we are saying here is that the left side was e to the 3 minus 2x. And so we know if the graph would look something like, not like that. The graph would have a y-intercept of e to the 3rd, which is like I don't know, 20, I'm going to guess. Something like that. And we're saying if we draw a line at 4, because the original equation is e to the 3 minus 2x is 4. So if we drew a line at 4, it's saying, where does that cross? And this is 3 halves minus ln of 2. Which would be about 0.8, I think. Okay. Let's see the next one. Okay, now we're going to do one that's a quadratic type. And you look at this, and you might be a little confused or worried. You see an e to the 2x and e to the x. How do we do that separately? How do we deal with this thing? We got e to the x in two different places. Well, if you notice that when you square e to the x, you get e to the 2x, then you realize this has the shape of a quadratic, only it's got e to the x instead of just x. So I'm going to do what's called a u substitution. And physically writing this out is optional, but it's such a common technique that once problems get more complicated, you usually do need to write it out just to keep track. So let's make up a new variable u, a new variable, and say it's equal to e to the x. So this would give me u squared minus u minus 6 equals 0. And then this is a quadratic. You solve it out the same way you would any other quadratic. And when I first saw a quadratic that didn't have x, I was confused the first time. Like, you're allowed to use just any other letter? Yeah, you are. So we have two cases here. Case 1, u equals 3. And case 2, u equals minus 2. So we have e to the x equals 3. That means x is natural log of 3. And then over here we have e to the x equals negative 2. Well, negative 2 is not in the range of the exponential function, so no solution there. So this is my only solution. See, what we kind of have here is if this were considered the g function, g of x is e to the x. And f of x is x squared minus x minus 6. Then if we do a composition, f of g of x, that would be f of e to the x, and you would plug in e to the x here, and it would give me what we started with. So yeah, this u substitution is when you have a composition of functions. You have a function inside another function, you basically write in a u there, or you do it in your head if you prefer, but I like to write it out. And then you sort of treat that as its own thing and solve for it first, and then you crack it open and solve for the x that you started with. The key is that the u is always the inside function. Alright, so let's keep going. Here we've got kind of an ugly looking equation, but we've got it set equal to 0, so factoring is always a good idea when we have an equation set to 0. So let's say, look at that, what's a common factor? Well, x, but also e to the x. Let's write it out. We have 3x e to the x plus x squared e to the x equals 0. Factor out the greatest common factor would be x e to the x. And then we'll be left with 3 plus x equals 0. So we've got three factors here, really. X equals 0, e to the x equals 0, or 3 plus x equals 0. Well, this one's already solved. This one has no solution. E to the x cannot be made to equal 0. This one has x equals negative 3. So my solution set is 0 and negative 3. Alright, so we've been doing exponential function using logs to undo them. We can do the opposite. Just like with exponential, since logs are one-to-one, if we can write it as one log equals another log, and they have the same base, then we can just say the things inside are the same as well. So let's show how that works. Log x squared plus 1 equals log x minus 2 plus log of x plus 3. And no base is stated, so we're assuming the base for all these is 10, even though that's just the rule. If you don't see a base stated, it says log, we assume it's base 10. So, the right side has two logs added. We said when we want to combine two logs together, the operation gets more complicated, so this becomes x minus 2, x plus 3. And the left side is still log of x squared plus 1. And that means they're just equal. Or you can imagine they're both powers of 10, but, well, I'll explain that in a minute. So we get x squared plus 1 equals, let's expand this out, x squared plus 3x minus 2x, so plus x minus 6. Those subtract from both sides, we get x equals 7. That's my only solution. And if we plug this back in, here we get 49 plus 1 is 50, log 50. And over here we would get 5 and 10, and 5 times 10 is also 50. So these both give the same thing, thanks to log rules. So, yeah, if they're already written as logs of the same form or exponentials of the same form, we can try to combine them. But if not, we're going to use exponents to undo the logarithm. So, natural log of x equals 8. Now, since this means log base e of x is 8, you could rewrite it as e to the 8 equals x, and just say, oh, that's my answer. And if you just look at this and you can easily see it, then you're welcome to just write that out. Me, though, I like to think of it as an operation we are doing. In the past, we have undone square roots or cube roots by raising both sides to a power. But now, we're going to make these both be powers and put the same base under them. We're going to say this is, instead of ln of x, it's e to the ln of x. And instead of 8, it's e to the 8. And this is a valid algebraic operation. You can apply e as a base and make them both powers, and the equation is still true. So then the e and the natural log undo each other. They cancel out if you call it that. You get x equals e to the 8. So this is an operation I want you to be comfortable with, that you can just put a big number down into the left of another number, and suddenly the thing you were dealing with is now a power. And that's perfectly legal to do. As long as your base is a positive number that's not 1, because we've said exponentials for negatives or for 1 are not defined, or for 0. So, let's see, what about that? There's log base 2 of 25 minus x equals 3. So we do the same thing, but in this case, since the base is 2, we will write a 2 underneath it. That'll be our base of our exponent. So, log base 2, 25 minus x equals 3. Let's put a big 2 underneath both. Big 2. Big 2. That 2 and that log 2 undo each other, and we're left with 25 minus x equals 2 to the third, which is 8. So 17 equals x. That's my answer. So now that we have this operation, we can combine it to solve with other operations, solve more complicated logs and exponents equations. And if you're not sure, just remember we're doing the order of operations backwards. So let's consider this problem here. We have 4 plus 3 log of 2x equals 16. Did I copy that right? Yes. So remember order of operations. Really MD are on one line and AS are on the other, because they're supposed to be the same priority. All right. Do we have any additions or subtractions? Yes, we have this plus 4. So we undo it. And our goal is to get the x by itself. So we're undoing things in reverse order until the x is isolated. Now, do I have any multiplication or division? Yes, there's a times 3 outside. There's also times 2, but it's inside the parentheses, so it comes last. Log of 2x equals 4. Now, do we have any exponents? Well, yes, a log, it counts as an exponent. It's the same type of creature. So we undo it. The base is implied 10, so put a big 10 under here. And so we get 2x equals 10,000. And divide by 2, x is 5,000. Okay, let's see what's next. We have log x plus 2 plus log x minus 1 equals 1. My thought is I'm going to combine these two into a single logarithm. So let's say it is log x plus 2 plus log x minus 1 equals 1. Combine these as log of x plus 2 x minus 1 equals 1. And now, base is 10, so I put a big 10 underneath. And I'll go ahead and expand this. X squared plus x minus 2 equals 10. So x squared plus x minus 12 equals 0. X plus 4, x minus 3 equals 0. So x equals negative 4 or 3. Now with these, we have to check for what are called extraneous roots. You may remember this coming up back when you learned about dealing with square roots, that sometimes in the process of solving, you create a new solution that doesn't work in the original. So let's plug these in. Log of negative 4 plus 2. Wait, that's log of a negative. We're not allowed to have log of a negative. This is undefined. So this negative 4 is not a real solution. But if we check 3, log 3 plus 2 plus log of 3 minus 1 equals 1. So that's log of 6, no, not 6, 5. Log of 5 plus log of 2 equals 1. Well, that's log 10, implied base 10, so that is a true statement. So 3 turns out to be the only solution. So yeah, this could definitely happen on a test. I'd give you a problem and you'd get an extraneous solution. You have to go back and check to make sure that it works in the original equation. All right, let's do another one. We're almost done with the raw problems, and I want to do a few application types. X squared equals 2, natural log of x plus 2. Oh, we got x's in two different places here. How would we solve this? Can we isolate the x? X squared equals natural log of x plus 2. There's a 2 here. We could divide by 2. X squared over 2 equals natural log x plus 2. And we could do a power of e to undo that natural log, and e to the x squared over 2 equals x plus 2, but it doesn't help, though, because I still got an x squared here and an x here, and yeah, I don't think this one's going to be solvable. And you might think, what about quadratic formula? Well, the problem with that is this x is inside a log, and this x is not. So that doesn't work. We'd have to somehow put them on the same level, and I don't see a way to do that. So with a problem like this, I would just say let's graph it. Let's just go to Desmos. We have x squared, and we have 2 ln of x plus 2. As we see, there are a couple solutions. There is this one and this one. So x is negative 0.712-ish, and x is 1.601-ish. In real life, you very often will not be able to get nice, neat analytic solutions. You will have to settle for a decimal round off. We prefer an actual solution, an exact one, but sometimes that's just not an option. Is there a way to solve this problem for real? Possibly. I don't know how, though. It's not off the top of my head. If there is, it would involve some advanced techniques that are not appropriate to this class, so I would be careful on a test not to give you any problem that you can't solve by hand. But on the homework, maybe there might be one or two where you need a calculator to do a decimal. All right. That's about doubling time. So, interest. We've talked about interest. A sum of $5,000 invested at 5% per year. Let's find the time required to double. So, I would say, okay. If it's compounded monthly, so monthly, we would get A of t is 5,001 plus 0.05 over 12 to the 12t, and I want to know when is it equal to 10,000. Well, I divide by 5,000 on both sides. So I get 1 plus 0.05 over 12 to the 12t equals 2. And then I would say, okay, well, I need to find this, I need to put a log on both sides. And this thing's a little weird looking. I don't know what exactly that base is. So I'm just going to use natural log. So the 12t comes down in front. I get 12t natural log of 1 plus 0.05 over 12 equals natural log of 2. And then t equals natural log of 2 over basically everything else. 12, 1 plus 0.05 over 12. Then you type that into a calculator and you get a number. I'm not going to work that one out. I'm going to work out the continuous one, though. But you can type that in a calculator if you want it. It should be pretty similar. A little less. Let's do the continuous form. If it's continuous, that whole thing goes down to PE to the RT. So in this case, that's 5,000 e to the 0.05t would equal 10,000. We want to find the time. So divide by 5,000 both sides, you get e to the 0.05t equals 2, which means 0.05t equals natural log of 2. So t would be natural log 2 over 0.05, which comes out to about 13.86 years. And I'll tell you a shortcut, because a lot of times you'll see like a news report says, oh, the growth rate is such and such, and it's maybe hard to visualize. What does a 5% growth rate really mean? Natural log 2 is about 0.70. So if we times 100, we would get 70 over 5 is 14. And so the approximation, the doubling time, is always about 70 divided by r as a percent. So that's an estimate. If you read in a newspaper, it says, oh, the population of this town is growing 2% every year, well, that means in 35 years it'll be twice as big. The interest is 7% a year. That means in 10 years it'll be twice as much you owe. So it's just a shorthand. It's not exact, but it's a useful rule of thumb to estimate. All right, now I want to do two similar problems, similar to that doubling time. And so this is the 4.6, the modeling section. So I don't want you to go through this and do every single one of these. I'm going to do a couple of these. I might put one like this on a test or a quiz. Yeah, it would be fair to put one like this on a quiz this week. But yeah, these models can get more complicated, so what I'm saying is you don't need to worry about ones that are any more complicated than what I do here. A bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in the colony. So find a model for the population after t hours. How many are there after 15 hours, and when will the count reach 100,000? Now, with real-life data, not money, we assume growth is always continuous. So the model is always going to be of the form n of t, or whatever variable you're choosing to use, is n naught, n0, meaning the amount there was at the start. In money, we call that the principal, but it's just saying whatever there was at the start time. Times e times r to the t, or to the power of rt. T is a variable. It stays as t unless we have a number to plug in. But n naught and r can be solved for or are given to us. So let's see if we can solve it. Okay. We were told it starts with 1,000. So that means n of t must be 1,000 e to the rt. Now, we were also told that it doubles every 3 hours. So we can say, well, 2,000 equals 1,000 e to the 3r. It doubles every 3 hours. So then 2 equals e to the 3r. It's another doubling time, so it looks pretty similar to the last thing we did. Natural log of 2 equals 3r. So r is natural log 2 over 3. So our model could be written then as n of t is 1,000 e to the natural log 2 over 3 t. So natural log 2 over 3 is the r. It's the rate. That's one way to write it. Now, there is a second way you could do this. We could say, well, this would become 1,000 e to the natural log of 2 to the t over 3. because a power to another power is same as multiply. This is natural log 2 times t over 3. We can sort of factor t over 3 out as a second exponent. And then that e and the natural log cancel each other out, and we're left with 1,000 times 2 to the t over 3. And so this is an alternate version. This is sort of the standard model here, I would say. And this is the doubling time model. So the doubling time version would be n of t is n naught times 2t divided by the doubling time, whatever that is. In this case, it's 3. So, with that said, then we have our model. We were asked a couple of computation questions. So, pull out a calculator here. All right. So, you can use either one of these models. If I'd wanted to use this one, in this case, I think using a decimal would make sense because you're going to have to type this into a calculator. So I could say, well, what is ln of 2 over 3? ln 2 over 3. Put that in parentheses just in case. About 0.23. So yeah, you could say this is about 1,000 e to the 0.23t. Or you could say it's 1,002 to the t over 3. They will come out to the same thing, is my point. Alright, so then the question was, how many are there after 15 hours? So if we type in 15, 1,000 e to the 0.23 times 15. Alright, so let's see. E to the 0.23 times 15. Let's see if it... about 31.5. And then that's times 1,000, so that means 31,500. And if I were to do it the other model here, I would get n of t is 1,000 times 2 to the 15 divided by 3 is 5. So that gives me 32,000. So you see, they're slightly different. Because I rounded ln 2 over 3, I rounded off to 0.23. So the answers are slightly different. In this case, I suppose this one's probably more precise than the one with the 2 in it. When will it reach 100,000? So then I have to set it equal. I have to say, okay, let's take one of these set equal to 100,000. All right. So equals, I'll use the doubling one, 1,000 times 2 to the t over 3. Divide by 1,000. 100 equals 2 to the t over 3. Now I'm going to need to use a log to get that t out of there. So I'll put log. I'll just use standard common log here because that way it's just a 2 on the left. 2 equals log of 2t over 3 equals t over 3 log of 2. So then t would equal times 3 is 6 over log 2. So then type that into the calculator. 6 over log 2, or 6 over 0.7 should be about, I'm going to say around 85. Let's find out. 6 over log of 2. Wait, 90. It's about 20? Oh. 6 over 0.7, 6 over 62. Yeah, okay. I did it. All right, so it's about 20 hours. That feels right. After 15, it was at 32,000. So after 18, it'll be at 64. We saw that, right? We said when we plugged in 15, we got 32,000. It doubles every 3 hours. So after 18, it would be 64,000. At 21, it'd be 128,000. So it fits that it's in between 18 and 21. I don't know why I said 90 earlier. I was probably trying to do it in my head, and it didn't. I messed it up. That's why we use calculators. All right, one last one. Half-life. Now, the half-life function, the half-life works the exact same way. So instead of saying how long will it take to double, it's saying how long will it take to cut in half. The process is the same. There's that same natural log of 2 involved. So if you were given a percent, you could just do divide by 70 divided by that percent to get the half-life. So here we're saying a sample is 300 milligrams. And this polonium, it cuts in half every 140 days. So I'm just going to write 140 there as H. And try to keep in mind that we're dealing with days and not hours or years or anything like that. So the model then would be... Let's pull it up. M of t equals 300. And then it was, let's check again. I forgot already. 2 to the negative t over 140. And I'll make a little note. T is days. M is milligrams. Now let's see. What were the questions that were asked? We wanted to... Okay, so there's a function. Find the mass after 1 year. Okay, so 1 year is 365 days. Two to the negative 365 over 140. So let's go ahead and type that in. Two to the parentheses negative 365 over 140. And then times 300. 49.2. Yeah, and if I were to list half-lives, so after 140 days, we should expect 150 milligrams. Then after 280 days, we expect 75. Another 140 would be 420, and there we'd expect 37.5. So we picked a number between, we got a number in between. So that makes sense. This is how you can sort of gut check your answers in case you lost a decimal or something. You can see if the answer you got fits. How long would it take to decay 200 milligrams? So we would set that equal to 200. 200 equals 300 times 2 to the negative t over 140. There's a multiplication. There's an exponent. Order of operations says we undo the multiplication first. 300. So we get 2/3 equals 2 to the negative t over 140. And I will put I'll just do ln on both sides. I could use log 2, but either way, one of them is going to be not cancel out. So I'll just use the ln for both. ln of 2/3 equals negative t over 140. So t is negative 140 ln of 2/3. How's that negative? Well, remember, if you put a number less than 1 into a log, you get a negative. So this will give us 2 negatives that will become a positive. So ln of 2/3, and then times 140, and then we'll just make it negative in our head, be 56.8. So 56.8, 200. This is if we want to make a whole table of t versus m. Those are some of the values we've found. And then we're asked to draw a graph. Okay, so let's draw a graph. And so we can use some of these numbers we found here to guide it. We can say, all right, we know that at 0, it's 300. We know that at 140, it's 150, and we don't have to try to make these fit the same scale. They probably will not. 280 as 75. And so these will decay downward. This to the left is kind of hypothetical. It's saying this hunk of polonium probably was bigger in the past, and so if you go back and say how much was there before. This is our graph. Okay, that about sums it up. So thank you for your time. I will see you in class.